Oh hey, I didn't see you there. I was just mining through some of your data, and I got some serious questions about your purchasing behavior. But we're gonna save that for another day. Did you know that your personal information becomes public every time you donate money to a political campaign? Hello world, my name is Data Mining Mike. I'm your friendly neighborhood data miner, and today we're gonna talk about how much money can you donate to a political campaign. I mined through over 6 million rows of political donations, and I have some amazing insights that are gonna add to your voter awareness. In this video, we are gonna cover the following questions. How many unique political donors are there in Washington state? What are the top 30 names of the most frequent donors? Which donors have contributed the largest sums of money throughout the year? Who is the top donor of all time? Given 4 machine learning models, can we predict the average donation per year? I am highly confident at the end of the spirit of instruction, you will be able to take what you've learned and apply it to your voter awareness, and that's called value. And because of that, you should like this video. Remember that sharing is caring. Subscribing is what winners do, but smashing the bell is what legends do. This channel breeds legends. But you can follow along with the scholarly blog article in the video description below. There it will give you all the Python code and dataset, so you can replicate the findings yourself. And that's called science. But first, AI news.
Because I create AI or machine learning models, people ask me all the time, what company should I invest in to make money? And I tell them, Iron Mountain, ticker symbol IRM. Iron Mountain is a real estate investment trust or REIT that owns the server farms that run ChatGPT. Other great companies are Google, Microsoft, IBM, and even Toyota.
Let's mine through the data in Python.
Data containing necessary variables about donations in Washington state can be sourced from data.gov. Data.gov is an open source repository / organization that hosts the datasets for every state. For instructional purposes and the fact that I live in Washington state, we will explore Washington state data as the example. The dataset contains 6,136,766 rows before any rows were removed and 35 columns. The dataset is limited to 19 years of Washington state campaign contributions spanning 2007 to 2025. The dataset has multiple columns for possible exploration. Due to extreme sparsity in the majority of variables, delimitations for the study are 3 columns of the dataset will be used, as they factor due to data relevance and cleanliness, the filer name, amount, and election year. However, only 2 variables will factor into predictions, amount and year. Okay, so in this Jupyter notebook, I'm going to be going over the data. For the sake of simplicity, I'm not going to run every single cell because that's just going to take too long to compile, especially when it comes to the neural net. But in this cell right here, I imported all the necessary libraries, and in some of the further cells I just have the model with it for simplicity's sake. If you want to just simply copy and paste, that's up to you. It makes it easier. But of course, I'm importing TensorFlow, I'm importing Gradient Booster, I'm importing Random Forest, Standard Scalar, R2 Score, and MSE Score, and of course Pandas, NumPy, and Seaborn, and Matplotlib for visualizations. In this cell I import the data set, in this cell I import the head, and so it shows the entire output of the columns. And so in this cell right here, I explore what columns there are, so it shows me which columns and what the column names are going to be. In this cell right here, I inspect the shape, so I know it's 6 million, over 6 million, and it's got 36 columns. And in this cell right here, I start the cleaning process. So I know I want to keep filer name, election year, and amount. So I create a new data frame, call it DF, and only keeping those specific columns. In here it shows that output. Now I drop all the columns that have empty values with the dropna function in order to produce a clean value. Then in this cell right here, I run the describe function. The describe function gives me all the descriptive statistics, and it's showing that it's showing that the amount for the mean is going to be like $286 per donor. But we know that that's not going to be the case because the average household, when I was going through the Excel sheet, is not donating that. They're donating more like $5 a household. So no one is donating $268 for whatever political campaign. Now, as we visualize the distribution. So I just cleaned the data. Now we're going into the exploratory data analysis part of it, where we see with the human eye how the data is laying out. and we test the distributions to see what machine learning models we need to use next. Because if the data is parametric or non-parametric, is going to determine what machine learning models we're going to be able to use. We see the distribution of the amount column, and the distribution is left skewed. And I can also tell here, as I put it here in this histogram, it only gives me one bin, and this bin is at less than the 0 mark. And I know that there was some return. So if you can ask for a refund on political donations. I didn't know that, but that seems evident in the data set itself because people were refunded money, but still that wasn't enough to move it to a negative portion. So I had to run the absolute. So I used the absolute function in order to get the absolute amounts and put it past 0 to get a more accurate number. So it's saying that the mean is $291 per donor, which is totally incorrect. No average household is donating that much to a political campaign. Now we use the frequency distribution of election year, and here it shows all the certain spikes of the years. In order to get a better visual of it, I just put it in this more colorful histogram chart so we can see that 2010, 2018, 2025, these were higher years. And there's really no trend. It really doesn't show a bell-shaped curve. It doesn't show any sort of skew one direction or the other. It really just looks random. And that's the thing about this data set is there is a continuous beating heart of donation money, but it is random. Now I'm inspecting the names of political donors. So there is 9,629 unique political donors. Most of them are super PACs. In this cell, I get the top 30 by running the value counts on filer name. And here's the output. We have Washington Education Association Political Action Committee, or the Teachers Union. Then the Firefighters Action Support Team, FAST PAC, Washington Real Estate Political Action Committee. They're pretty frequent. International Brotherhood of Electrical Workers, Joe Murphy PAC, Washington State Troopers, Washington Association, Rossi, Dino J, whoever they are, Jay Inslee, the governor, Nucor PAC, Seattle Firefighters. And you can see all these PACs yourself in the blog, but I'm not going to go naming them all. But now I have the output of the top 20, and the top 20 largest donors by sum. No on 1631, and you can go through them yourself. They really don't mean much to me. I went through them to see whether or not they passed or failed, and just based off these 20, and of these 20, most of them failed. So people are spending a lot of money just to try to get things pushed for marketing, to try to get the voters to vote on something, and it's just not going to pass. It's just most of the time it's not passing. So your return on investment for, it seems, for these political donations is not going very well, according to the data, to get these initiatives voted for. I also found some interesting things like Coca-Cola is a big donor. But here we have the top 5 donors overall. So the top 5 PACs for Washington State. If we look at it, the Washington Education Political Action Committee, so the Teachers Union, trailing along is the Realtors Political Action Committee. All right, everybody else is a trailing distance away. So we can tell that a Realtors Political Action Committee didn't start matching or trying to pace the teachers union until around 2015 here. And then after that, they've just been slowly trailing behind, but literally it looks like they've been trying to match. But before that, they didn't really seem to care. So something happened at this year for this PAC to start trying to chase this PAC. Either way, now I'm dropping all the outliers, standardize the data set. Now I'm going to test for normality with the Shapiro-Wilk test. It's important to test these variables for normality to ensure machine learning models you're going to use are the correct machine learning models. And we want to, either way, it didn't test positive. It is not Gaussian. It is not normally distributed. It is not parametric. It is non-parametric. It is going to require non-parametric machine learning models. One non-parametric machine learning model I'll just drop it into is the neural net. So I'm dropping it into the neural net. I'm trying to predict the amount, the target variable given the election year, the feature variable. I run test train split. So test train split is a tuple that creates 4 variables, X, train, X test, Y train, Y test. And here is the meat and potatoes of the neural net itself. I'm only running 4 layers. I don't really need to run that many. It's not like adding more layers is going to increase the accuracy, and I did play around with that, and it didn't. So it's like it's either you got a good data set or you don't, and in this case I don't, but it's still interesting to see the way it played out. But either way, my model compiler here, I have it stopping after 10 epochs in order to save computation time. So after 10 epochs, if there isn't a big reduction in model loss, it'll just stop, and else it'll just could be a runaway loop on epochs or just take forever just to train. But either way, it scored horribly. The RSME, you want it as close to 0 as possible. It's like way out there, like 42 mil. Like, no, it is not good at predicting anything. And so I created the predictions for the next 10 years, $233 per household, per donor. So next, I'm calling in an ensemble method. So with the ensemble method, I'm running multiple regression trees. So this is the gradient boost regressor. So gradient boost is I'm running 100 different trees at the learning rate of 10% and maximum depth of one tree in random state of 0. I throw in the X train, X test, or I'm sorry, the X train and Y train, and I predict the X test. And it gives me my output, and it's random. It looks random. It looks just like the visualization of the data above. Totally random. It has a horrible RSME score. It has a horrible R2 score. The R2 you want as close to 1 as possible. This is like 4 zeros away because you put 1, 2, 3, 4, 5. And yeah, it's just a bad score. Now I run polynomial linear regression. That's another model I can run given the non-parametric nature of the data set itself. So here are the specific libraries just in case you needed them. I'm running 2 degrees, so 2 features. Here's all the code you need running X and Y. Here is the same output, garbage. MSE is horrible, even worse, and the R2 is even worse. So now I'm running LOAS. LOAS doesn't really give you a score. It's just a confirmation of how does it represent itself visually. It does not actually give you a score. But in final analysis, how many unique political donors? There was 9,629. Top 30 most frequent names were already outputted. And you could check those out in the blog. Which donors have contributed the largest sums of money? The above output rendered 5 packs. So we know the Political Action Committee and the Teachers Union. The Teachers Union is winning, while the Firefighters Action Support Team is in a distant third. The highest of all time, Washington Education Political Action Committee. Given the 4 models, neural net, gradient booster, polynomial regression, and LOAS, can we accurately predict? No. We accept the null hypothesis that the frequency distribution of political donations is random and does not demonstrate any patterns. If the alternative hypothesis were true, given the data set, one of the 4 predictive models would have yielded a more accurate result. The data was visibly left skewed toward the 0 mark and tested negative for being Gaussian. In fact, it had to be coerced to the absolute value in order to make it more workable. The neural net had an accuracy of over 42 million for the MSE when it should be as close to 0 as possible. And lastly, the LOAS indicated a horrible fit and random residuals near the 0 mark.
Given the 4 models of a neural net, gradient booster, LOAS, and polynomial regression, none of these models could yield any accurate prediction for a voter donation, even though there was over 6 million instances. This just goes to show that because you have a big data set doesn't mean you're gonna make an accurate model. There's a lot of people out there that claim that they have all these machine learning models or AI that can predict all this crap. They're a bunch of freaking liars. You always need to be diligent and trust the science yourself. But the one thing this science shows is, 1, there is a beating heart of voter donations that is going to be going 2 campaigns every single year, okay? There is always gonna be that. But if somebody comes out and tells you, oh, you can predict how much the political donations are gonna be, they're a liar. And they don't know what they're talking about because I got 6.6 million rows that say otherwise. Also, we accept the null hypothesis that the frequency distribution of voter donations is random and does not demonstrate any patterns. If the alternative hypothesis were true, then that means one of the 4 models would have given a more accurate prediction. And also going through the data visually, it shows that it is totally random. And that's one of the biggest things about data analysis is seeing how does the data lay out visually in the graphs. Once again, you can replicate the findings yourself by checking out the link to the blog in the video description below, and that's called Science. Thank you for watching the video all the way to the end. My name is Data Mining Mike. Be sure to like, subscribe, and smash that bell for more data-driven updates. Bye!